Now this is question 8 from the June 15 International C34 paper. It's differentiation, a little bit of trig identities there. It's basically, if you know your chain rule pretty well, then it should be no problem, part A. Having said that, having looked at some of the responses from students, there have been some misunderstandings of the chain rule. It might be worth mentioning that first of all. I saw this quite a bit. Just knowing that the Lund differentiates to 1 over, and just doing that. But of course that doesn't work because it's not Ln y or whatever, it's a Ln of a function of y. So basically it's chain rule. So that if we're doing d by dx of some function of x using the chain rule, that's going to be that function of x times by 1 over x, times by, because Ln differentiates to 1 over x, but here we've got fx, it'll be that. So that was missed by some people. So that was one point where some people slipped up. So let's just get on with it. D by dy Ln tangent 2y equals to, as what tangent 2y is differentiated, so that's 2 sec squared 2y all over tan 2y, because tan 2y, tan differentiates to sec squared, but we've got almost like a chain rule thing within that. The 2 is there because it's sec tan 2y, so that we must have a 2 there. Now a few of you got there, but then proceeded to do some strange things like, well, I saw particularly a few people expanding the angle, the 2y, so using the expansion for 2y, so tangent 2y equals 2 tan y over 1 minus tangent squared y. It's a useful formula, but it's not useful here because we're trying to get to 4y, so it's hard to know how going to a smaller angle, to breaking it down to something even smaller when we're heading for sine 4y is going to help. I think because we're looking for sine 4y, it might be worth reverting to base functions at some point. But what I'm going to do is just keep the 2 on the top, and sec squared is cos squared on the bottom. The tangent 2y, of course, is equal to sine 2y over cos 2y. I'm reluctant to write this kind of stack fraction thing, but I'll relent on this occasion. So what we can then do is just multiply this out, and we can see that on the bottom we have cos 2y sine 2y. Now this is really good because hopefully you can see it, and you really should see that the cos 2y and sine 2y, or you should know the basically identity for 2x. There's certain things that you should be seeing, we see so often that we should see them in both directions. So we should see that this is equal to this, and that sine x cos x is equal to sine 2x over 2. So we've done it. That equals to 2 sine 2x over 2. Oh, do you know what? I don't really want to do a stack fraction again, so what I'm going to do is double both bits. There you go. Done. quite a lot of you wrote some nice answers to that. But there were some people that got, as I say, the most common thing was getting differentiation wrong by not doing the chain rule right in the first place, and then doing some strange things with the angle. Okay, so a few people, by the way, did change the tangent to what I have seen this, which wasn't a bad approach, changing this to sine 2y over cos 2y, and then because logs are quite nice in this, and that gives you ln sine 2y minus ln cos 2y, and that worked quite nicely as well. So nothing wrong with that. Quite a few people did it that way. Okay, now part B wasn't actually on the mock paper, that the ones that I marked from Havant College, but it's actually from the original paper it came from. It's a differential equation, and I thought it's quite worth looking at this, because actually it's a good example where the first part is really leading into the second part, which isn't always the case, but very, very often is. It's something we should certainly be expecting, and if it's not, we need to be a little bit surprised. Sometimes it won't be, but when part B looks like a separate question, you should be thinking, oh, it's a separate question. But there we go. Okay, so let's separate the variables. 1 over sine 4y dy integral is equal to 2 cos x dx. Now, sine 4y there is cosec 4y, and you can use the formula in the formula book to do that, because there's a formula for cosec 4y involving a ln, but we've got a much handier thing here, ln tangent 2y. We've been asked to show it, ln tan 2y, so we should be using that. Now, so that it would be a quarter of that at this stage, wouldn't it? Because that would be a quarter of, because we had a 4 on the top of this, that would be a quarter of ln tangent 2y. Don't need a modulus here, by the way, because of the range of y that's given. So we did a modulus sign is totally redundant here, for those of you who were tempted to put it. And that's 2 sine x plus c. Okay. I suppose we could just times by 4 at this stage and just do ln tangent 2y is equal to 8 sine x plus c dash, if you don't like the fact that it's a different c. Okay, now we're told that when y is pi by 6, x is 0. So when y equals pi by 6, x equals 0. So we have ln tan pi by 6 is equal to 8 sine 0 plus c dash. Ln of tangent pi, it's not pi by 6, is it? Because it's double pi by 6, so that's pi by 3. The tangent to pi by 3 is the square root of 3. Is c dash. So we can go back and we can write our solution. But they do want us to do a bit of work on this. So we can go back to our original thing here. So we've got ln of tangent 2y equals 8 sine x plus ln the square root of 3. Take the ln the square root of 3 over ln tangent 2y minus ln the square root of 3 equals 8 sine x. And then we can use the rule of logs. Ln tangent 2y over the square root of 3 equals 8 sine x. So that gives us tangent 2y over the square root of 3 is equal to E8 sine x. So clearly we've got tangent 2y equals to the square root of 3 E8 sine x. So there we go. It's a good example of one question leading nicely to the next bit. Okay. Turned out to be reasonably okay in the end, just going through the motions really. So it's just knowing your stuff, and also, as I say, I think this is a nice example of where using an earlier part where you've had to differentiate, you could use in an integration problem in the final, in the next bit. Okay, so that's something to be watching for. Okay, that's it.